Hello students, welcome to Educate. Today we are going to start with second book of physics class 11th, chapter number 8, entitled as Mechanical Properties of Solids. Here all that we are going to study is types of stress, all types of stress. What is stress? Stress is force upon area. So let's analyze first, and after that I will go in detail. Then we will study about strain, different type of strain. Strain means what? Change in dimension divided by original dimension. After that we will study Hooke's law, which tells that within elastic limit stress is proportional to strain. After that we will study Young's modulus, which will be stress, normal stress divided by longitudinal strain. Don't worry, I will tell you in detail. This is just a quick summary what we are going to study. Then bulk modulus, BULK, bulk modulus, which will be stress, here volumetric strain, then another will be shear modulus, which means shearing force or shearing stress, divided by shearing strain. Then we will see energy stored in a stretched wire, and lastly we will see Poisson's ratio, which will be equal to lateral strain. There is no sign here. Lateral strain divided by longitudinal strain. So here, after having a look on these things that lesson is about, you must have curiosity to know about these terms and how they are related. So we are going to analyze them one by one. The very first thing is, it is stress. So what is stress? Stress equal to force upon area. So if we write units, force is in Newton, area will be meter square. which is also equal to Pascal, if you remember. Then various type of stress. So let's see the types. So type can be tensile stress. Tensile means when one end is fixed, another end is free, and force is applied to pull it, so that there is elongation. Then another is compressional stress, when body is compressed. Another one is hydrostatic, when from all sides equal forces are applied. And last one is shearing stress. Due to shearing stress, body will get deformed. So these are the types of stress, and then comes the types of strain. So there are different type of strains. So strain means change in dimension divided by original dimension, right? So here if you write the units, change in dimension, suppose you are taking length upon length, so it will be dimensionless. Suppose you are taking volume upon volume, means meter cube upon meter cube, so that will also be dimensionless. So we can say that strain has no dimension. Then comes types of strains. So first one is longitudinal. It means when length increases, suppose after applying force there is increase in length delta L. So longitudinal strain will be delta L divided by L. Then comes volumetric strain. It means change in volume divided by original volume. Then comes shearing strain, which means deformation produced. So suppose deformation is delta x and the original size is L. So these are different types of stress and strains. Now you have understood. Now we are going to check the ratio of stress and strain. Thereby we will get different types of moduli. Like when we talk about Young's modulus, YOUNGS, Young's modulus, denoted as Y. So this will be equal to stress, normal stress, divided by longitudinal strain. So normal stress is force upon area divided by delta L upon L. If you write force, suppose you are given this is a wire, and here you are putting some weights. So in that case, force can be written as mg, and A will be area of cross section of the wire. So here you can further write mg divided by A times delta L, A times delta L into L. So Young's modulus is like this. Similarly, if you write bulk modulus, suppose we denote it as B. So force upon area divided by change in volume delta V divided by V. Here one thing is noticeable. Suppose this is original radius and now it is compressed. So when compression takes place, then suppose radius reduces to r dash, in that case volume will decrease. So when we find change in volume, so it will be negative minus delta V, because new volume will be less than original volume. So here there will be negative sign. One more thing we can do, force upon area can be written as pressure. So we can write it as minus pressure into volume divided by change in volume. So this is bulk modulus. Now if we consider shear modulus, its notation may vary. We can denote it here time being as eta. In some books it will be theta. So whatever notation you use, that does not matter, but you have to write what you are noting. So in this case, force upon area will be deforming force divided by deformation produced delta x by L, but delta x can be taken as delta L. So eta will be equal to F upon A delta L upon L. So these are basic points that you must know before studying the lesson. Now we are going to start with the lesson. We will see different aspects. There is another term, elastic limit. So what is that? Elastic limit means if you are applying deforming force and body regains its shape, so what is the maximum value of deforming force up to which body regains its shape? That will be the elastic limit. Now Hooke's law is defined within the elastic limit. Here different type of stress and strains are shown. You can read them, shearing, strain, etc. that you have understood. Here on the book, when pressure is applied, it gets deformed from where shearing stress will be there. Here also, then original shape is like this. When this type of force is applied, tangential force, then there will be deformation. Here in this case, what is happening? Original length is L, and now on applying force on both the sides, it gets stretched by delta L. So it becomes L plus delta L. So this is how here what is happening. From all sides, force is being applied, and then final size becomes like this. So these are aspects we have to explore. And the shearing strain can also be written as like this delta x divided by L. So from here also it can be concluded this angle is theta. This is L, this delta x, so it will become perpendicular upon base. So this will give tan theta. So these are things you will see. Now let's proceed. The hydraulic stress is also given here. You can understand it. And then volumetric strain, I told you. Then Hooke's law. So what is Hooke's law? Hooke's law means within elastic limit, stress is proportional to strain. Right? So there must be a constant for making it equal. So stress equal to a constant, say y equal to strain. Sorry, into strain. And here y is Young's modulus, from where we write stress upon strain equal to Young's modulus, and stress is force upon area divided by, here we are taking longitudinal strain, so delta L divided by L. Now, if we plot the graph between stress and strain, so how will it look like? So obviously, since it is proportional, so it will be straight line. If here we write stress, or we can write load applied, and here we write strain, then graph will look like this. But there is a limit. After that limit, what will happen? So here we will study the graph. Stress will be plotted along y-axis and strain will be plotted along x-axis, and then we will see. So that is also good concept. In this curve here, if you observe it carefully, there are different points. This is stress, this is strain. Now when stress is applied, so there is here up to this point, strain is proportional to stress, but point A is proportional limit. Again we increase the stress, then there is more increment than proportional limit in the length. Then again this is yield point, and after that, if body is further subjected to, means if the wire is further subjected to stress, then it reaches to point B, and then after that it will not come back to original position, it will have permanent extension, and beyond that even slighter stress is applied, the strain will be more, and after reaching point D, what will happen? The wire will start stretching on its own, means due to its own weight, and at this point wire will break. So I think you have understood the graph. Now let's read it to make it more clear. The relation between the stress and the strain for a given material under tensile stress can be found experimentally. In a standard test of tensile properties, a test cylinder or a wire is stretched by an applied force. The fractional change in the length, the strain, and the applied force needed to cause the strain are recorded. The applied force is gradually increased in a step and the change in the length is noted. A graph is plotted between the stress, which is equal in magnitude to the applied force per unit area, and the strain produced. A typical graph for a metal as shown in figure. Analogous graph for compression and shear stress may also be obtained. The stress strain curves vary from material to material. These curves help us to understand how a given material deforms with increasing loads. From the graph, we can see that in the region between O to A here, the curve is linear. In this region, Hooke's law is obeyed. The body regains its original dimensions when the applied force is removed. It's clear. In this region, the solid behaves as an elastic body up to here. Then what happens? After that, in the region from A to B, from here to here, stress and the strain are not proportional. Nevertheless, the body still returns to its original dimension when the load is removed from here to here. But the point B in the curve is known as yield point, also known as elastic limit, and the corresponding stress is known as yield strength. Right? If the load is increased further, the stress developed exceeds the yield strength and the strain increases rapidly. Even for a small change in the stress, the proportion of the curve between B and C, as you have seen, proportion of the curve between B and D shows when the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this case, even when the stress is zero, the strain is not zero. The material is said to have a permanent set, as I explained you. The deformation is said to be the plastic deformation. The point D on the graph is the ultimate tensile strength of the material. Beyond this point, additional strain is produced even by reduced applied force and the fracture occurs at point E. If the ultimate strength and the fracture point D and E are close, the material is said to be brittle. If they are far apart, the material is said to be ductile. So you have understood? Brittle means it will break at once. Ductile means wire can be drawn from it. So these are some basic properties that are required. Here there is graph. This is stress, this is strain, stress strain curve for elastic tissue of aorta, the large tube vessel carrying blood from the heart. So here you have to see, as I stated earlier, the stress strain behavior varies from material to material. For example, rubber can be pulled to several times its original length and still returns to its original shape. So figure 8.3 shows stress strain curve for the elastic tissue of aorta present in the heart. Note that although elastic region is very large, the material does not obey Hooke's law over most of the region. It's obvious because the curve is not straight here, it is curved, not straight line. So secondly, there is no well-defined plastic region. Substances like tissue of aorta, rubber, etc., which can be stretched to cause large strains are called elastomers. This is also one important definition. It means those materials which can be stretched to large strains, they are called elastomers. Here, elastic moduli, modulus of elasticity as Young's modulus, as I told you, bulk modulus and shear modulus. So I have already told you about these things. Here, Young's modulus is compressive ratio of the tensile or compressive stress to the longitudinal strain. Here notations are different. You can use the one you like. So y equal to sigma divided by E. So we can put the value F upon A whole divided by delta L upon L. So we will get this thing. Since the strain is dimensionless quantity, as I told you, the unit of Young's modulus is same as that of the stress, or N Newton per meter square or Pascal. Here in this table, you will see the various values. Like aluminum, density is this much. Young modulus for aluminum is 70 into 10 power 9 Newton per meter square. For copper it is 110, for iron it is 190, for steel it is 200, for glass it is 65. Substances, the substance tested under compression. And then concrete this much, wood this much, bone this much, polystyrene this much, and ultimate strength like 110 into 10 power 6. This is stress, maximum stress, 400. So what do you observe? Which material has highest Young's modulus here? So that is steel. And here if you find ultimate strength, this is also that of steel. And what about this? Yield strength, this is also that of steel. Now, let's see next thing. Here same information is given as we have read from the table. Now there is one question. The question says a structural steel rod has a radius of 10 millimeter and a length of 1 meter. A 100 kilonewton force stretches it along its length. Calculate stress, elongation and strain on the rod. Young's modulus of the structural steel is given. So let's write the information. R is given as 10 millimeter. It means we can write it 10 into 10 power minus 3 meter. We need area of cross section, so we can apply pi r square. So pi times this will become 10 power minus 2 whole square, correct, meter square. Then next point is force is 100 kilonewton. F is given as 100 kilo. Kilo stands for 1000. So 100 into 1000 Newton. This is force. Then what more is given? Length of A rod is given as 1 meter, and we need stress. So stress is force upon area. Just put the values. Force is this much, area is this much. Just divide, you will get answer. That will be 3.18 into 10 power 8. 3.18 into 10 power 8 Newton per meter square. Then we need a strain. Strain is simple. Change in length divided by original length. Here, change in length is not given. Then what option is left? We have another option. We can apply the formula of Young's modulus. So that gives y equal to stress. Sorry, y equal to stress divided by strain. So our concern is to get strain. So strain equal to stress divided by Young's modulus. Stress we have already found. Young's modulus is given 2 into 10 power 11. So we can evaluate. Now suppose you have got this value and you need delta L. So since strain equal to delta L upon L, so whatever value you have got, multiply by L, and L is 1 meter, so it will remain same. So next point is, only 3 things were there: elongation, strain, and the rod. So everything we have got. So I think you have understood. Let's go to next question. Next question says, a copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both have diameter 3.0 millimeter, are connected end to end. When stretched by a load, the net elongation is found to be 0.7 millimeter. Obtain the load applied. This is very important question for your exam. So you have to be very careful. Situation I am going to show you. Suppose there are 2 wires. Here there is load. Right. A copper wire of 2.2 meters. This is 2.2 meter. Young's modulus of copper will be given. We can use from the table. And then next 1.6 meter of steel wire. This is 1.6 meter steel wire. And Y steel we have, it is 2 into 10 to the power 11 that we have used, but still we can use the table if need be. Now other information, elongation, delta L is given 0.7 millimeter, that is 10 to the power minus 3 meter. Now what is the load applied? Load is to be found. So what we can do here, on applying, we assume that this weight of this wire is negligible. So if we apply load here, then what would happen? If we apply load, if you assume this as a base and then we apply load, then what would happen? What would be the elongation produced in the 2 cases? And then we find a sum. Since sum is given, we can easily evaluate. So let's find it in simplest way. So here the copper and steel wires are under a tensile stress because they have the same tension equal to the load and the same area of cross section, as we have already discussed. So stress equal to strain into Young's modulus. Therefore we can find these values. So we find the ratio, and so let's explain you because it is little complicated. So what do? We first write Young modulus of steel divided by Young modulus of copper. We write the formula: force upon area, right, for steel divided by delta L steel divided by length of steel wire multiplied by, for this value we write F upon A, then here delta L copper divided by length of copper, right? I think you have understood. Here F upon A term will cancel out, and young moduli of the two materials are given, so we can write it 2.0 into 10 to the power 11 divided by 1.1 into 10 to the power 11. So this 20 upon 11 will be left, and here delta L copper, delta L Cu divided by, here we can do one thing, delta L copper, and this will come in denominator L copper, and this delta L steel, delta L steel into L steel, right? So here we keep delta L Cu divided by delta L steel intact, and we put the values. LS, length of steel wire, that is 2 point, it is how much? Length of steel wire is 1.6 and that of copper is 2.2. So we can put those values. So so 1.6 divided by 2.2, right? And here 10 power 11, 10 power 11 cancels. So this is 20 upon 11 delta L Cu divided by delta L steel into 16 by 22. We create a relation. So what will be the relation? So a relation will be, we will get the values from here, one ratio will be there, and then since we have another ratio, another relation delta Ls plus delta L copper. In our question it is given, it is somewhere it's given, it is 7 into 10 to power 7.0 into 10 to the power minus 4. So we have two relations and two equations. We can solve them, and then we will get the values delta LC and delta LS, and after that we can use formula like F equal to sorry, not F, Y, just write Y steel equal to F upon A divided by delta L steel divided by L steel. Since you have got the value of delta L steel in calculation and length of steel is given, area of cross section is given, Young modulus is given, you can calculate F, and that is to be found. I think you have understood, but I'm going to analyze once again so that thing may become very clear, because something remained unclear. So in order to give you clarity, once again I would like to start from beginning. So what we did, we started from here, we were given delta L steel plus delta L copper equal to, it is 0.7 mm, 0.7 into 10 to the power minus 3. This is equation number 1. And what is our purpose? We have to find out F. So formula is, you can use either for steel, Ys equal to F upon A divided by delta L steel divided by L steel. So here, first what will we do? First we will try to find out delta L steel. Similarly for copper also same thing can be done. F upon A will be same, only delta L copper divided by length copper These two are different. So what will be our step? As I told you, first of all, we write the two formula together and we divide it, we put the values. So one equation in delta L and delta L steel and delta L copper we have. Another relation in terms of ratio we will get for delta L copper, delta L steel, and then we can solve the two equations. If we solve, we will get the value of delta ls and delta lcu, and then you can take any value either for copper or for steel and then analyze. I think you can do. Let's consider this question. In a human pyramid in a circus, here situation is shown. If it is clear, so this is human pyramid. So the question is, in a human pyramid in a circus, the entire weight of the balanced group is supported by the legs of a performer who is lying on his back. As shown in the figure, the combined mass of all the persons performing the act and the tables, blocks, etc. involved is 280 kg. The mass of the performer lying on his back at the bottom of the pyramid is 60 kg. Each thigh bone femur of this performer has a length of 50 centimeter and an effective radius of 2 centimeter. Determine the amount by which each thigh bone gets compressed under the extra load. Here, compression is to be found in the thigh bone femur, whose dimension is given as 50 centimeter and radius is given 2 centimeter. So in order to get the required value, we will be needing the Young modulus of thigh bone that we will make use from the table. So let's see how to solve. It's given total mass of all the performers, tables, blocks, etc. 280 kg. Mass of the performer is 60 kg. Mass supported by the legs of the performer at the bottom of the pyramid will be, you have to reduce the weight of the person who is holding all. So 280 minus 60, so 220 kg. Now weight of this supported mass, so just convert it into weight, means you have to multiply by 9.8, so you will get 2156 Newton. Weight supported by each thigh bone, there are 2 thigh bones, so half of this, so that is 1078 Newton. Now we have to check in the table. So Young modulus for bone is 9.4 into 10 power 9 Newton per meter square. Now we have sufficient information. We have weight, that is mg, and or you can say f, and Young modulus is also given, length is given, radius of thigh bone is given. From here you can get area, so pi r square, right? Now apply the formula. Your concern is to get delta L. So with these informations you can easily get Young modulus equal to F divided by A times delta L divided by L. And your purpose is to get delta L. So write delta L here and F into L divided by Y into A. Put the values. You can easily calculate. Here value is 4.55 into 10 power minus 5 meter. So this is a very small change. The fractional decrease in thigh bone is 0.0091%, which is very, very less. So I think you have understood. Now next question is, not next question, next concept. As I told you that suppose this is the block and force is applied, so it is displaced through this distance. It is displaced like this. So this delta x, original shape is given. So here we can determine theta, tan theta, or just write x upon L. So we will get shearing strain. Shearing strain, that will be delta x divided by L. L will be psi. So let's read what is given. We have already discussed about it. The ratio of shearing stress to compression to corresponding shearing strain is called the shear modulus of the material and is denoted by G. In some books you will find it is denoted as eta also. So it's okay, that does not matter. So G equal to shearing stress divided by shearing strain. Shearing stress is just force per unit area, so force upon area divided by delta x upon L. Just simplify, F into L divided by A into delta x. So here, either in terms of theta also you can write the same thing when you have written tan theta, or when theta is small, so tan theta will become theta. So this can be also written like this. So this expression we will get. And as far as unit is concerned, so here theta will have no unit. So force upon area, force is Newton, and area will have meter square. So that. Now here there is one statement here you can read. It can be seen that the shear modulus or modulus of rigidity is generally less than Young modulus. You can observe from the table, but you don't have to memorize. That does not matter. Now we have one question. A square lead slab of side 50 centimeter and thickness 10 centimeter is subject to a shearing force on its narrow face, shown here, here force is 9 into 10 power 4 Newton. The lower edge is riveted to the floor. How much will the upper edge be displaced? Here delta x is to be found. So information is given, just we have to decipher it. So for that we can analyze, solution is given. The lead slab is fixed and the force is applied parallel to the narrow face as shown in the figure like this. So area of the face 50 centimeter and 10 centimeter, so that will be 0.05 meter square. So stress we can calculate, force upon area. So this will be the stress, and we know that shearing strain, so delta x, whatever displacement is there, and original length, so we can write, and then we can put it in the formula to get the answer. What is the formula? Formula you know, shearing stress, here shearing modulus, say we write G, so force upon area times delta x upon L, right? Your concern is to get delta x. So delta x will be equal to F into L divided by G into A. And then after putting values, you will get this much, 0.16 millimeter. I think you have understood it. Now, here definition of bulk modulus is given. As I told you in the beginning of the lesson, that in this case we take bulk modulus, say B. So force upon area will be taken, but we will make it pressure, change in volume. So here this is original, and then after compression its volume decreases. So change in volume will be negative, delta V negative divided by V. If we write it as pressure, so B equal to minus PV divided by delta V. So this is bulk modulus. Here one more important term we can define, the inverse of bulk modulus, that will be called compressibility. So we can read these facts here. In section 8.3 we have seen that when a body is submerged in a fluid, it undergoes a hydraulic stress equal in magnitude to the hydraulic pressure. This leads to the decrease in the volume of the body, thus producing a strain called volumetric strain. The ratio of hydraulic stress to the corresponding hydraulic strain is called bulk modulus. It is denoted by symbol B, as I explained you. So the negative sign indicates that this fact that with increase in pressure, a decrease in volume occurs. That is, if P is positive, delta V is negative. Thus, for a system in equilibrium, the value of bulk modulus B is always positive. SI, unit of bulk modulus, is the same as that of pressure, Newton per meter square or Pascal. The bulk moduli of few common materials are given in the table that you can see. The reciprocal, as I told you, just inverse it. So the reciprocal of bulk modulus is called compressibility and is denoted by K. It is defined as the fractional change in volume per unit increase in pressure. 1 upon B, we put the values, we get this thing. It can be seen from the data given in the table that bulk moduli for solids are much larger than the liquids, which are again much larger than bulk modulus for the gases. So these are basic ideas. Here table is given stress, strain, various elastic moduli, tensiles or compressive stress force upon area, shearing stress force upon area, hydraulic forces perpendicular everywhere to all the surfaces. So all things as we have studied up to now, that is summarized here also. And this table is useful for you. I think you must go through it. Now, here there is some information. Let's see what is given. The solids are the least compressible, whereas the gases are the most compressible. Gases are about 1,000,000 times more compressible than solids. Gases have large compressibilities which vary with pressure and the temperature. The incompressibility of the solids is primarily due to the tight coupling between the neighboring atoms. The molecules in liquids are also bound with their neighbors, but not as strong as in solids. Molecules in gases are very poorly coupled to their neighbors. So table is given which shows the various types of stress, strain, elastic moduli and the applicable state of matter. Right. So up to here, up to here you have studied about various types of moduli, their formula and the related numericals. Now we are going to see one numerical based on bulk modulus. Here the average depth of Indian Ocean is about 3000 meters. Right. So what would be the pressure? If you remember, if we find pressure of a liquid column, so formula is rho GH. Rho is density, G is acceleration due to gravity, and H is height of column. Right. So here person is in water, suppose 3000 meters. So there will be pressure, and that can be evaluated by taking density of water as 1000, G 9.8 and height is 3000. After putting these all values, we will be able to get pressure. And in bulk modulus, if you remember, we need pressure into volume divided by change in volume. Then question will become easier. So first step was this, that we can do. So here the same thing is done, and we have got 3 into 10 power 7 Newton per meter square. Now second thing left is we have to find out delta V upon V. So it is very simple. Then we can write P equal to, you can ignore minus sign, just write P delta V upon V. So keep delta V upon V this side and B in this side. So delta V upon V in magnitudes, negative sign we can neglect. So pressure divided by bulk modulus. Bulk modulus of the material must be given. Here it is given 2.28 to 10 power 9 Newton per meter square. Hence, you will get this much value. And if you want to say it in terms of percentage, obviously 10 power minus 2, it means 1.36 divided by 100. So that would be the percentage value, 1.36%. So this is all for this lecture. We will continue with the next topic in next lecture. Thank you for watching. Team Educate.